We present multimodal virtual point 3D detection. This is joint work by Tianwei, Xingyi, Zhou, and Philipp Krähenbühl. We first have a 2-minute summary of our method. The full version will start after this. We know that LiDAR measurements are often sparse. Specifically, here we project LiDAR points onto the camera images. We can see that for faraway objects, like these few pedestrians on the right, they often only contain 3 or 4 LiDAR points per object. It is extremely challenging to differentiate these few LiDAR points from background points on the ground or estimate any box attributes like exact locations or dimensions. In our work, we address this sparsity problem through a method called multimodal virtual point. Let's see how our algorithm works. In the first step, we run a 2D instant segmentation on camera images. The segmentation masks help us identify 2D pixels and 3D points that correspond to this object. In the second step, we randomly sample virtual pixels inside the foreground segmentation mask. Then in step 3, we perform nearest neighbor depth interpolation between sampled virtual pixel and projected real LiDAR points. Each pixel will get its depth from close-by LiDAR measurements. With each pixel's depth information, we can lift them into 3D virtual point cloud. These 3D virtual point clouds are much denser than the original LiDAR measurements and contain detailed geometric structure of the object. We can then pass these 3D virtual points and real LiDAR points into an off-the-shelf 3D detector to get a 3D bounding box prediction with more detailed location and box dimension estimation. For the main evaluation, we compare with other published entries on the NeurIPS Leaderboard. Our method achieves state-of-the-art results and improves previous best published method by more than 5 NeurIPS detection score. We'll now start with the full version of this presentation. Over the last 2 years, we have seen great progress in Lidar-based 3D detection. On the Waymo dataset, the 3D detection accuracy has been improved by 20 MAP from the popular point pillar detector to the recent centerpoint detector. However, the performance at long range is still unsatisfactory. Here, we visualize a few failure cases of the state-of-the-art centerpoint detector on the NeurIPS dataset. One common error is false positive detection shown in these 3 blue circles. The 3D detector misrecognizes background LiDAR points as 3D objects. Another common error at long range is false negative detection shown in the orange circle. The detector completely misses the 3D objects and classifies it as background. Additionally, the box attribute regression is often inaccurate for faraway objects. The predicted box is often misoriented, and the dimension is often off by a certain degree. In our understanding, the main reason for this failure mode is the sparsity of the LiDAR measurements. While the depth measurement returned from the LiDAR sensor is extremely accurate, it only contains limited number of points, making it hard for any detector to recognize them as foreground objects or turn them into accurate oriented 3D bounding boxes. To understand this sparsity issue better, we project LiDAR points onto the camera images. We can see that faraway objects, like these few pedestrians on the right, only contain 3 or 4 LiDAR points per object. It is extremely challenging to differentiate these few LiDAR points from background points on the ground or estimate any box attributes like exact locations or dimensions. One potential solution is to augment the LiDAR point cloud with higher resolution RGB sensor information. These RGB pixel measurements are much denser than the projected point cloud shown in white dots and contain semantic information useful for object recognition. For example, we can run a 2D instance segmentation model on these camera images and get a semantic label for each pixel. One previous approach called point painting utilizes this idea. The model first runs 2D instance segmentation on the camera images. After that, the model projects the sparse LiDAR point cloud onto the images to get a corresponding semantic label. These painted LiDAR points, 3D points with the semantic labels, are passed into standard 3D detection model to get the 3D bounding box predictions. As we already know that these few LiDAR points correspond to the pedestrian class, the 3D detector is able to tell that there is a pedestrian at this rough location. However, as we still only get 3 LiDAR points for this object, the predicted box parameter won't be accurate. To solve this problem, we proposed to also estimate the detailed 3D shape from 2D mask prediction by lifting 2D pixels into 3D. Concretely, similar to point painting, we first run a 2D instance segmentation on camera images to get a semantic segmentation mask and identify foreground LiDAR points correspond to this object, shown as the red dots in the image. We then randomly sample 2D pixels inside the instance segmentation mask. In order to lift this pixel into 3D virtual points, we need to know about the corresponding depths at each pixel location. In our work, we interpolate these depth values from existing LiDAR measurements. Specifically, we perform a nearest neighbor matching between randomly sampled foreground pixels and projected LiDAR points. After that, foreground pixel will get the depth from close-by LiDAR measurements, and we can then lift them into 3D space. This leads to our paper's main idea, called multimodal virtual point. Let's recap how our algorithm works. In the first step, we run a 2D instance segmentation on camera images. The segmentation mask helps us to identify 2D pixels and 3D points that correspond to this object. In the second step, we randomly sample virtual pixels inside the foreground segmentation mask. Then, in step 3, we perform nearest neighbor depth interpolation between sampled virtual pixels and projected real LiDAR points. Each pixel will get its depth from close-by LiDAR measurement. With each pixel's depth information, we can lift them into 3D virtual point cloud. These point clouds are much denser than the original LiDAR measurements and contain detailed geometric structure of the object. We can then pass these virtual points and real LiDAR points into an off-the-shelf 3D detector to get a 3D bounding boxes with more detailed location and box dimension estimations. Let's see how our approach works in practice. We are given a sparse LiDAR point cloud. We will then run our virtual point generation algorithm to augment the sparse point cloud. The augmented point cloud is 10x denser at object locations and only introduce less than 50% more virtual LiDAR points. Now, let's see how these points look like at the long range. On the right, we visualize the bottom vehicle shown in the blue circle. The original LiDAR point clouds shown at the top contain 10 LiDAR measurements, while our augmented LiDAR point cloud shown at the bottom contains hundreds of LiDAR points. This denser point cloud includes detailed 3D structure, enabling better vehicle shape and location estimation. Similarly, we also visualize one pedestrian object shown in the blue circle. The original LiDAR points only contains 5 measurements, while our augmented point cloud are 20x denser and contain detailed 3D geometry information that is helpful for downstream detection tasks. During the inference, we'll first generate the augmented point cloud using the virtual point generation algorithm described above. This augmented point cloud will be then passed into an off-the-shelf 3D detector to get the 3D bounding box predictions. Let's see how our model performs on the popular NeurIPS benchmark. Here we compare with state-of-the-art LiDAR-only center-point detector with a VoxelNet backbone. We show the detection accuracy comparison across different detection ranges. When the number of points is large enough, like the 0 to 50 meters range, our model is 2 MAP better than the center point baseline. When the LiDAR point cloud is sparser, like the 15 to 30 meter range or 30 to 50 meter range, our model achieves a significant 7 to 10 MAP improvement. We also experiment with another popular point pillar backbone. The improvements still hold and will achieve 7 to 11 MAP improvements across different detection ranges. In the end, we also compare with other published entries on the NeurIPS Leaderboard. Our method achieves state-of-the-art results and improves previous best published method by more than 5 NeurIPS detection score. Code and pre-trained model are all available on our website. Now, let's see a visualization of our model's detection output.